keep it on. Okay, so I just want to say that please, when you ask questions, please try to use the microphone. So there's a microphone with him and there's one with me. So you can just wait and we'll pass the mic. Okay, so it's a great pleasure to have Prabha Mandayam from, she's a professor at IIT Madras, and she will give lectures on Bell's inequality and, and entanglement.
Thank you. Thank you for inviting me here and for having me as a part of the School of Statistical Physics this year. So the brief given to me was to talk about I guess I will have to write bigger is what I realize. Let me try that. All right. So the plan is to, over the next 5 lectures, give you some overview and understanding of quantum entanglement, and in particular dwell a little bit on the so-called Bell inequalities, or maybe the Bell CHSH inequalities, right? And thank you to the organizers for also accommodating my travel constraints. So I am unable to be here for the entire week. So it's going to be sort of compressed, but you know, quantum information can be compressed very well. So we're going to try to do this over the next 3 days, 5 lectures, and hopefully, you know, it will not be too rushed. I will try to make it as pedagogically, you know, structured as possible. So the plan is to do this, where today, in the 2 lectures that I'm going to be giving today, I first want to talk a little bit about the density operator framework in quantum mechanics. This is something that I find is often not dwelt upon in a typical even graduate level quantum mechanics course. I know almost many of you are graduate students here who have obviously done graduate level courses in quantum mechanics, but the notion of a density operator is something that we perhaps often encounter first in the context of statistical physics, right? But today I'm just going to introduce it in the context of quantum mechanics itself, and of course Professor Gregory is going to talk about this in the context of statistical physics as well. So there's going to be some interesting overlaps maybe between what I'm going to talk about today and his lectures as well, which will be nice to see the same thing from multiple perspectives, as it were. So today, in this first lecture, I want to talk about the density operator framework and also hopefully introduce a central player in this, which is the von Neumann entropy. Okay. In the second lecture today, I want to, now I'm not talking about multiple systems here, right? This is just, it could be a single quantum system that I'm talking about, but in the next lecture, I will actually move on to talking about bipartite quantum systems. Again, I want to introduce a little bit the mathematical language in which we talk about bipartite quantum systems, in particular the idea of a tensor product. Then, of course, the notion of being entangled naturally comes in when one starts talking about multiple systems, right? So the way I want to introduce this is actually through the notion of something called a Schmidt decomposition. And this will also lead us to a very sort of natural way to measure entanglement or correlations, which is the so-called subsystem von Neumann entropy. I'm sort of writing all this down so that some of you will remind me if I don't actually touch upon some of these things. I don't know, is there a bottom line that I should draw? Is this okay for people at the back as well? Okay. Then tomorrow, having introduced bipartite systems and Schmidt decomposition, I would actually like to talk about the Bell-CHSH inequalities. This will pretty much form the entire lecture tomorrow. And in the process, we will encounter some of the names that you probably have associated with this, the so-called EPR paradox and Cyrillson's bound. And having introduced Bell states, I would then like to, on Wednesday, talk a little bit about, so this idea of Bell states, which are somewhat important in the context of quantum information and quantum computation today. Since we have seen a little bit about these states, it may be nice to ask what kind of properties do they have which are different from classical systems, and so what can you do with them, which maybe you cannot do using classical systems. So in particular, I want to talk a little bit about, of course, this fancy word, teleportation. I also want to talk about something called super dense coding. So the first one I think of as a computational task, the second one I think of as an information theoretic or a communication task. And then in the context of Bell states, I also want to talk a little bit about not just entanglement in states, but entanglement in the context of operators. So, or entanglement, let's say, in the context of unitary evolutions. What do I need to prepare a Bell state, right? And that will also then bring us to, I'm sorry, let me just say, the idea of entangling unitary operations, or unitary operations that give rise to that, let's say, that are a resource in order for us to be able to prepare entanglement, okay? The final lecture on Wednesday, I want to talk about, so all of this discussion, let's say starting today afternoon all the way down here, is going to be focused on what we call pure states. Of course, all of us have some intuitive idea of what a pure state is. Today's lecture, hopefully, we'll pin that down more precisely. But then what about mixed states, right? The Bell states, which many of you have seen, or the kind of entangled states that one typically writes down, are all pure entangled states. So what about mixed states? How does one talk about entanglement in the context of mixed states? This leads us to some very interesting mathematical questions and some answers which are already known in the community. And one of these is the so-called Perez-Horodeczki criterion for identifying when a mixed state is entangled, okay? And this will also then lead us to a discussion on entanglement measures. How does one quantify entanglement? And I would like to mention at least two of them, which are often used in the literature. Maybe you have heard of these, but it may be nice to see these definitions and understand them in the context of specific examples, the concurrence and the negativity. Okay, so this is sort of the plan. All right, so today I want to just talk about the density operator, right? So in a standard, at least first graduate level course on quantum mechanics, we start off, well, if you are like me, the school of thought which says quantum mechanics is to be taught using postulates or in an axiomatic way, then the first postulate that you will state is that the state of a quantum system is a unit vector in a Hilbert space, right? So quantum states, we associate them with unit vectors in Hilbert spaces. So for most of my lectures here, I mean maybe all of it, I'm going to be looking at finite dimensional spaces. So I'm just going to sort of say, let's say that I have a d-dimensional quantum system, then I'm going to associate basically this complex linear vector space of d dimensions with this, yeah? Bigger font, yeah, okay, I will try to keep that in mind. So for a d-dimensional, so this is just notation because I'm going to be sort of using this very often. So it's just a d-dimensional complex linear vector space. All of us know what that is, yes? And then we say that quantum states are supposed to be unit vectors in this, and we have some physical motivation for why we say that quantum states, that this is the mathematical sort of structure of quantum states, right? And then we have some notation for this. So typically we use this so-called ket vector, right, or the ket. So I say that psi belongs to CD, and these two lines for me indicate the norm of the vector. This is 1, right? Its length is 1, okay? So this is the sort of standard picture that one has of quantum states, right? But now I'm going to talk about two instances where this mathematical sort of identification is not sufficient for us to be able to describe certain physical operations or certain physical phenomena, okay? And the first of these is actually measurement. So at least the way I like to think about why we need density matrices or density operators is to think about measurement. So I'm going to start erasing stuff here. I hope that's okay. So what happens in a quantum measurement? We know that you measure observables which are Hermitian operators. So associated with every observable is some orthonormal basis. And post-measurement, I'm going to observe one of these orthonormal states as my post-measurement state, okay? So I'm going to draw a picture to talk about measurement. So I'm going to imagine that it's a kind of box, okay? So I want to measure some observable A, and A some Hermitian operator, so it has associated with it some set of orthonormal states, which are basically its eigenstates. So I'm going to just label them as this set AI. There's some arbitrary state that I measure, okay? This could be of whatever dimension. If it's some d-dimensional space, typically these are matrices, d cross d Hermitian matrices, right? So then you know that you have d orthogonal states possible. So maybe I goes from 1 to d, okay? And associated with these states are a set of eigenvalues which constitute the allowed set of values for this observable to take. Those are your set of outcomes, right? So then maybe I call them lambda I. So these are the eigenstates. These are the eigenvalues of this observable A. And I have some measurement device which is going to perform this measurement. And then at the end of it, I observe a final post-measurement state, okay? What is the post-measurement state? Yeah. Oh, The thicker one? Okay. Yeah. All right. Better? Okay, let's see. Yeah. I'll try to write, yeah. Oh, the thicker one was better. I don't know if there are more of those. Okay, so what is this post-measurement state? How would you describe this post-measurement state? Yeah? One of the eigenvectors. But that's not a mathematical description for me. Yeah? So let's say that you perform this measurement once. Okay? You get the eigenstate A1. So the outcome or the value lambda 1 is observed. And so you know by this so-called collapse postulate that then the state that was the post-measurement state must be A1. But then you prepare your same state again, you repeat this process, and then you have a different outcome, right? And indeed, depending on a certain probability distribution, which comes from the overlap or the coefficients that you get when you decompose this state in this basis, right, that constitutes a probability distribution for you. So you can think of the probability of getting outcome I in state psi is this, okay? So depending on what this distribution is, you basically get a set of states here, right, which are realized according to this probability distribution. So you already see that this idea of quantum state as just a vector in a Hilbert space is no longer going to suffice if you want to describe this post-measurement state. If you have each instance, at each instance if you have observed, you know exactly what the state is. But if I want to talk about this post-measurement state without having observed this each time, right? So one way that people talk about this is to say that you do not have knowledge of the measurement outcome. It is a statistical process. So you know because you're measuring this observable, you know this probability distribution, you prepared the state, so you know psi, you know the set AI, you know this probability distribution. So it is basically like saying that I'm tossing a d-dimensional coin, if you will, according to some probability distribution. That is the process that you want to describe. Now what is the post-measurement state, right? So the post-measurement state, if I do not each time observe the state, but instead want to talk about this in the statistical sense, is actually an ensemble, right? It's a collection of states. So it's an ensemble, which I'm just going to write like this. I'm going to say that it's a set of states, AI, which are picked according to some probability distribution Pi, right? And how do I describe this kind of an ensemble? So this idea of states as vectors is okay so long as one is talking about pure states, okay? But now I have a mixture, and I'm going to say this is a convex mixture of pure states. So one way to describe this is then to think about what is really happening in this sort of output side. If I think about this as the initial state input and this is an output, then actually I need to draw several lines out here. There are several possibilities, and in each instance, yeah. So I'll come to this. For now, you can just think of it as a mixture over a set of, these states are mixed with weights according to a probability distribution, right? So I know that PIs are all greater than, lie between 0 and 1, and that they sum to 1, okay? So I think of this as a convex set, right? I'll come back to the density matrix itself as belonging to a convex set. But for now, just say that this is what I mean. Let's just say that this is what I mean, okay? So the way to make this association is to give this ensemble itself a mathematical description, is to think about what are called projection operators, right? So at least this was sort of von Neumann's original way of understanding the measurement process, right? So where he says that think of the set of projectors that you would associate with these final states that you get, okay? So I'm going to use capital PI to denote a projection onto this ith eigenstate. Now, if my kets represent states or vectors, then in order to represent operators, you know that I need to go to the dual space, okay? And I hope you're all familiar with this kind of a notation. Yes? Everyone? So you know what this means. So you realize that this is what one may think of as an outer product, right? And this is an operator acting on this d-dimensional Hilbert space. Now, in particular, I want to think about these projection operators, AI, okay? So one way to think about this final state is then in terms of an operator, rho, which is basically, again, a weighted sum of these projectors weighted according to this probability distribution. And this is what one refers to as the density matrix or the density operator associated with this particular measurement operation. This is the density operator that describes the final state.
Excuse me.
Yes?
When you say this is a convex mixture,
Yeah.
You already said that the measurement, here.
Yeah.
Yeah, so you already said that we don't know what is the post state is.
Yes.
Because we're just taking in the initial state and then basically without looking at it, we are just combining it.
Yeah.
So is it still not a pure state? Like suppose the initial state was a pure state, it came in, now it's a mixture of state. Is that what you're saying?
So if you, in every instance, so first of all, what do I expect to get out of a quantum measurement? I expect to get some statistics out of it. I expect to get expectation values out of it, typically,
Yes.
right? And to get expectation values, essentially what I'm asking for is the probability distribution and so on, right? Mm-hmm. So in almost no situation am I going to be doing this a single time.
Yeah.
When I think of a quantum measurement, even today, I have a quantum computer, I think of measuring the final state. It's never a single shot, right? It's some very large n number of shots, which gives you some statistics using which you can reconstruct this final state, right? So what I want is now a statistical description of the final state. I don't want just these probabilities, which I know how to get according to this rule, but I now want a valid way to describe this post-measurement state in the statistical sense, not by telling me the outcome at each instance of this.
No, so let me clarify what I mean with an example.
Yeah.
Suppose we have a stream of Ag atoms coming in,
Yeah.
and we
yeah.
have a Stern-Gerlach
Yeah,
apparatus.
yeah.
So this will split it into two beams.
Right.
And if I were to actually put a screen, I
Yeah.
would know exactly what Ag atoms correspond to which spin, right? But suppose if I didn't look at it, and if I somehow make these beams come together and go again along with each other, then what is the final state? Is this a pure state or is it a mixture of states?
Yeah,
That's what
so it's good. So let's think about the Stern-Gerlach maybe. Yeah. So when you say that you send in this beam of silver atoms, right? So let's say you have this Stern-Gerlach setup, right? So there is some inhomogeneous magnetic field. There is a stream of silver atoms. This, of course, is a physical realization of that box that I just drew there. And then I have a screen. So you know that because the spin angular momentum is quantized, you do not expect to see a continuous distribution on the screen. You expect to see maybe some two distinct peaks on the screen, right? Now today, of course, Stern-Gerlach expected to see a continuous thing and all that. Now, this exactly is a probabilistic, is this ensemble picture, right? Because when I talk about the peaks, I'm not talking about a single silver atom. I'm not talking about where each silver atom went. For a given silver atom, I'm collapsing it into either the, so let's say that this is my Z direction. I'm collapsing it onto the up spin in the Z direction or the down spin in the Z direction for a single one. But when I send this entire beam, then I basically am splitting it up like this, right? And in doing so, what I have finally is not a pure state, but it's not the state of a single spin, right? It is now the state of this collection of a very large number of spins. And how do I describe that state? Let's say it's equally likely for them to go either way. So then I say half of them are up and half of them are down. So what I'm saying is this is a precise description of exactly that. So in a way, it's good to be here. So let's contrast. So if I claim that my final density matrix in this case is basically this, okay, it's half up and half down, okay. Contrast this with another state. Contrast this with a state of this form, which I'm going to call, let's say, plus, which is half up, 1 over root 2 up plus 1 over root 2 down. This is a pure state. This is a state which actually contains some relative phase information between these two states. This is still a coherent superposition of the spin being up and the spin being down. But once I've done this, suppose I started with this state. So let's do that. So let's say that I somehow managed to prepare all my silver atoms in the, so this, if you recognize, is actually an eigenstate of the spin X observable, okay? So I'm preparing all my spins, this could just be a beam of electrons for all I care, in the up spin of the X, of the sigma X operator, the Pauli X operator. And now I run a Stern-Gerlach experiment with the inhomogeneous magnetic field along the Z. Do I still retain the superposition?
If I were to observe it on a screen, definitely not. But my question is basically, suppose if I remove this screen and if I put another Stern-Gerlach with the reverse magnetic field, then I would get a beam of Ag atoms again. Will that be
So let's actually try that. So nice. So we can actually try that, no? So we know what's going to happen in a Stern-Gerlach setup. Oh, I see. So your question was, if I don't put the screen, am I then not making the observation and therefore am I not back to the pure state picture?
Yeah,
the short answer is no, and I will tell you why. So the idea of a measurement, or even a measurement box, the way I draw it, is very different from a unitary evolution. Okay, if I put some other operator here like U, which is actually just a unitary transformation, then yes, I am indeed preserving purity. I'm continuing, my state continues to be a pure state if it started out in a pure state. But in doing this kind of an operation, which forces my spin to now choose to say that, am I going to be in spin up Z, or am I going to be in spin down Z? So you can see this even with a single silver atom, right? Like if you think about preparing it not in the Z eigenstate, but in the X eigenstate, this superposition that you prepared is already broken by the time you have passed this atom through this experiment, right? Now you put another one, so we'll come to that. So let's say that you're doing this. So, sorry. Sequential Stern-Gerlach is a nice thing to talk about in general. So let's do that. So I'm now going to just call this some SGZ, okay? That's my Stern-Gerlach along Z. I prepared a superposition of the up and down spins, okay? And then let's say one of the two outcomes was realized. Which one was realized? You can pick. Okay, so let's say up, both are equally likely. And now your question is, I'm going to pass this through the same setup. Yeah? What happens?
It will remain in that state.
It will remain in that state. Absolutely. Because now I'm in an eigenstate of the operator that I'm measuring. So I have reached essentially a kind of fixed point for this process now. I'm going to always be in this up Z state. I'm never going to be able to go back to this superposition actually. So this.
No, but what I'm suggesting is like the second Stern-Gerlach is reversed. So
I'm just coming to that.
yeah,
so this is an irreversible process, right? Mathematically, because how do I again describe this mathematically? What has happened in going from here to here is I have projected onto this state. Okay? It's a projection operation. Yeah? So, for example, if I had a minus, or I could have had any arbitrary face out here. So I could have said plus some e to the I phi down Z over root 2, right? So I could have had any superposition here of up and down, right? The only thing that I have access to by repeating this many, many times is actually these probabilities. So I could have even put, need not be equal superposition, but whatever. But there is no way that I'm going to be able to extract this face information now. That is lost. So this is, in fact, a simplest example that you can think of decoherence. You started with a coherent superposition, and by performing a measurement, you have actually decohered the state. Right? You have lost this phase information. And when one talks about open quantum systems and so on, this is indeed the mechanism that one thinks of for decoherence, where now the measurement is not made on the system itself, but it's as if there's an observer in the environment or the bath who is actually performing these measurements and hence causing this decoherence. Okay?
By the way, why doesn't the same thing happen in Mach-Zehnder experiment on optics, where the single beam comes and the beam splitter basically splits into two parts?
The beam splitter is a unitary transformation.
Oh, okay, that's why. Okay.
The beam splitter is like a, what we think of as a quantum gate. It's a unitary transformation. The Stern-Gerlach is a measurement. And it is good to keep this difference in mind, that in one case, you're always preserving coherence and superpositions. In the other case, you're breaking coherence. And indeed, that is why you need a different way to describe this post-measurement state, now as an ensemble of pure states, right? And in this particular case of some observable A with a set of energy eigenstates AI, then this is the final density matrix, right? Which describes for me the post-measurement state. Okay, so, yeah.
So when you are calling it a convex mixture of pure states,
Yeah.
you are calling that ensemble is the convex mixture of these pure states.
Yes.
And another thing that this density matrix is kind of a linear combination of these projectors. Is it true to say?
Yeah, I can also write this, indeed. So we'll come to this, whether I can now, I'm going to sort of expand your question to say, is this association unique? Okay, so if I think of a particular density matrix, is there exactly one way of decomposing it as a set of pure states? I will address that question shortly. But yes, I can also write this as sum over I, lambda I pi, right? So it is indeed a sum of projections weighted by the same lambda I, and because, sorry, not lambda I, what did I say? Pi, I'm so sorry, yeah. So this is little pi and big pi, okay? So, yeah? These projectors weighted by these probability distributions. That's what this operator is, yeah.
The subsequent measurements are made in the X or the Y cases. Can we possibly get back the input state?
Yeah. I purposely did not talk about that, but we can do that, okay? So, again, that's something that you should tell me now. Okay, so now the question is, I don't want to do this boring sequential Stern-Gerlach where I'm all the time doing the Stern-Gerlach with the magnetic field in the Z direction. Let me tilt this and now alternate between, let's say, X and Z Stern-Gerlach setups, okay? So, I start with Z. Let's say I start with this distinct plus state which I have identified as a equal superposition of, as the plus half eigenstate of the sigma x operator, right? So let's say I again got this up spin, the plus half spin eigenstate here. Now I follow this up with a Stern-Gerlach with the inhomogeneous magnetic field in the x direction. This is now a measurement of a different observable, namely the sigma x observable. This was a measurement of the sigma z observable. So what do I expect to see as the possible outcomes for the sigma x measurement? It could be the eigenstates. So let me call them something. So let me say that plus and minus are the eigenstates of sigma x, and they are basically, when I write them in terms of the z basis, this is what they look like, yes? So I can invert this pair of linear equations and write my sigma z eigenstate as a superposition of the sigma x eigenstates, correct? So effectively this input state for the x observable now is an equal superposition of the spin up and spin down in the x direction. So what are the probabilities here? I expect to get both possibilities. I expect to get both plus and minus with equal probability. So this is probability half and probability half. Both outcomes are possible. The projection operator is something that I associate with a given measurement. Okay, it doesn't have to be sequential. This, so when I write this, I am saying that a particular projection was realized in this measurement. But this measurement itself is a combination of both projections. And which one occurs is really a probabilistic question. I don't know. I can only tell you that I could get up with probability half and down with probability half. So each measurement has its own set of projection operators associated with it. This one will have a pair of projections along the sigma x plus and minus eigenstates. And now I'm saying that both outcomes are equally likely. Yeah. So what has happened in doing this, so I started with an eigenstate of sigma x. I did not measure sigma x itself, rather I measured a different observable, and then I measured the sigma x. And by doing so, I have actually, in some sense, lost this information which I had originally about the sigma x observable, because I had prepared my state in the sigma x with a plus or the plus half eigenstate.
So the density matrix actually represents that as GZ. I mean, if you're preparing it accordingly.
No.
No.
So, okay, just to clarify, I'm going to write down something called a measurement process or a measurement operator, okay? The measurement operator associated with some observable A is a collection of projections Pi, okay? That's it. So this is my measurement operator. This is, I must warn you that this is a somewhat limited definition of measurement, but this is what, okay, let me say that this is what I call a projective measurement, okay? So a projective measurement is basically this operation which is described by a collection of projections Pi, okay? What must they satisfy? This set of projections must sum to the identity operator on the Hilbert space. And what would the product of two of these projections be? Delta ij followed by? What happens when I is equal to j? Huh? What is pi squared for any projection? Okay? All right. So this defines a projective measurement. Okay? There is no reference to the state, nor is there a reference to probabilities, because the probabilities are now induced once you reference this with a particular state. Once you say that I am measuring this observable on this state, that is when the probability distribution is induced. The measurement itself is just described by a collection of orthogonal projectors. The measurement is a box which for me outputs a set of probabilities and associated post-measurement states. How do I describe that box? By this collection of orthogonal projectors which have to span the space, so they sum to identity, and of course they are orthogonal, so they satisfy this. Yeah.
I'm sorry, what happens when you have two sequential Stern-Gerlachs in different directions, but you don't make a measurement in between?
Which means you don't observe this. You should realize that this actually does not care whether you as an observer peeked into this or not, right? So let's say I don't do this, good, okay? So maybe I do this with yellow chalk. So this is a situation where I don't know what outcome occurred here. So then what? What is my state of knowledge? I'm going to say, well, either could have happened. All right, that doesn't change this one, yeah? It's just that now if I did this measurement, I have some knowledge of this intermediate state. If I don't, I just say, well, it's an equal mixture of these two states. But having that mixture as an input state does not change the statistics here for me, because this mixture is still comprising of states which have equal weights on plus and minus. That's a good question. So what you're saying is basically, can a density matrix be, can I think of measurement on a density matrix? Indeed, you can. So all of the postulates that we write, we can extend them in the language of the density operator or the density matrix.
So one question, so my sigma z is a measurement that we are doing.
Yeah.
And it is different from this density operator that it this density operator has pi's, but sigma z doesn't has pi's, because we can write sigma z is equal to also up plus down. So how does it my sigma z is different from density operator?
Okay, so in this case, the observable A, is this okay or no? Yeah? So now you're talking about a spectral decomposition of the observable A. Yeah? How do I write the spectral decomposition? Yes, that's also a sum of projections. That's a sum of projections weighted by the eigenvalues, okay? And I still haven't come to mathematical properties of the density matrix, but we'll see that the density matrix is, has a slightly different mathematical property than the set of observables. The set of observables are Hermitian matrices, Hermitian operators on the space. So they have real eigenvalues. If you look at what I've written here, this matrix, this operator, this set Pi is actually a set of probabilities, okay? Which means not only are they real, but they are positive. I can in fact think of this, which I have written here, this representation for this density matrix as a spectral decomposition of some sort, right? It's as if I have expanded this row in this orthonormal basis, except that its eigenvalues are all positive now. Also, they sum to 1. So this then brings us to my next point, which was mathematical description of a density matrix. So I'll write that down formally. But interestingly, as you point out, if I measure an observable A, the density matrix that I get as the post-measurement state is an operator which is also diagonal in the same basis. Okay, indeed, it is diagonal in the same basis. But its eigenvalues are now positive semi-definite, could be, or positive if you assume that it has full rank, right? And the operator has trace 1. Okay, it's an operator of unit trace. Okay, so any further questions on the Stern-Gerlach stuff? Because I'm actually not going to dwell, I did not intend to dwell on this, but I guess this was still an interesting discussion to have to clarify things. So can I erase this part and we move on to, so maybe just one last thing I want to point out is just by playing around with these sequential Stern-Gerlach setups, one can actually understand some very nice foundational ideas like the idea of complementary observables, that you cannot simultaneously have information, accurate information about both the X operator and the sigma Z operator. And this exactly tells you that, because at this point, I knew exactly what my sigma X state was. But in attempting to get information about the sigma Z state by doing this measurement, I have actually, I'm actually now finally at a state where the knowledge of this has been completely erased in some sense. So suppose I started with this state, and suppose I did the Stern-Gerlach X measurement here itself. What is the output state? It's still plus, right? And what is the probability distribution? It's actually a delta distribution. It's a what you think of as a point mass or a delta distribution. There's only one, you always get the plus state with probability 1 and the minus state with probability 0. But in doing the intervening Z measurement, before doing this X measurement, you have now transformed this state into something where both plus and minus are now equally likely. That I think of as a state with maximal uncertainty as far as the sigma X observable is concerned, because both the outcomes are now equally likely. So in trying to get information about Z, I have completely garbled the information in X. Okay? So quantum mechanics fundamentally tells you that it is not possible to observe certain quantities accurately simultaneously. So in a way, you see the uncertainty principle come into play here. Okay? Okay, so a lot of digression, but I guess that's okay. So we move on to talking about the density operator a little bit more. So this idea of actually complementarity and the fact that you cannot have information exactly about multiple observables will actually feed very crucially into this Bell-CH-SH inequality, which we'll discuss tomorrow. Okay, so now let me define the density operator or the density matrix. So I'm going to use these terms somewhat interchangeably here. So it's basically, so this is, like I said, one way of thinking about why I need to expand my definition of a quantum state to go beyond just vectors, right? So now I'm going to say that the state of a quantum system is described by an operator rho which belongs to, so I'm going to say, okay, so let me say B of CD, okay? So earlier, remember I said it's just some psi belonging to CD, okay? That was my, in the vector form, so long as I was just thinking about pure states. But now I have to think about operators on the space, and this B is basically the set of bounded linear operators on the space. Since I'm talking finite dimensions, this is not strictly necessary. I could have just said the set of linear operators on the space. Some people just like to call this L to say that it's a set of linear operators on the space such that rho is positive semi-definite and trace rho is 1. Okay? So this defines a general quantum state for me. And one place to see why this is required is actually to think about a post-measurement state, right? And think about this ensemble of pure states. And basically the idea that you no longer have exact information about which pure state was realized, but rather you have only statistical knowledge of this. So how do you describe an ensemble? Well, you describe it so, okay? I hope everyone is familiar with the notion of positivity and so on, right? So one simple way to check is to say that the expectation value of the state is positive. So you take this expectation value with respect to any state, and then you'll realize that this is a sum of positive terms, and so this is a positive operator, okay? All right, so the other reason why one may need this notion of a density matrix is if you think about multiple quantum systems. Of course, we'll discuss this more in the afternoon today, but I just want to point this out. So I realized, as I was making some notes for this, that there are two ways in which people have approached the density operator framework. One is the von Neumann way, where he thinks in terms of measurement and asks, how do you actually give a statistical description of the post-measurement state, and that's what I have described so far. The other approach, I believe, actually is due to Lev Landau, who thought about how do you describe the state of an individual subsystem when you have a multi-party system, when you have multiple systems, okay, and you only have full knowledge of the entire system. So let's say there are two systems. It could think of it as system and bath, if you wish. Think of it as two, your box of ideal gas partitioned into two. You only have knowledge of the complete system, okay, and that is your vector description. That's your pure state. How do I then talk about the state of the individual subsystems? And intuitively, you already know that if there is some correlation between these two systems, then it is not as simple as saying that I have a pure state here and I have another pure state here. So in fact, the individual subsystems not being in pure states is a signature of the fact that you have some correlations between these systems. So that is the other reason why one may have to move beyond the state vector picture, okay? All right, so the next question, so would be, is this association of, so I wrote down the density matrix as this collection of pure states, right? But here I have now expanded the definition to talk about any linear operator which is trace 1 and which is positive semi-definite. So if I start from this picture, if I give you some operator which is positive trace 1, how do you associate an ensemble with this? I went from that to, I kind of then extracted these properties from that particular example that I had, right? And then I made it into a general description. So how do I now decompose this into an ensemble of pure states? Exactly, very nice. So one way to think about decomposing this is just do an eigen state decomposition, right? So since these are positive matrices, they basically have a spectral decomposition. So I could think about some, let me use some different letter. So let me say that this So one ensemble that I can always associate with any density matrix is this ensemble of eigenstates, where the associated probability distribution from which I'm picking these eigenstates is basically the set of eigenvalues of this density matrix. Okay? But now it turns out that this is not unique. Okay? That there could be multiple convex sums of pure states or multiple pure state mixtures which could actually lead to the same density matrix. The eigenspectrum is a special one where this set of pure states are actually orthogonal. But there could be other such ensembles which actually lead to the same density matrix, and I could give you some examples and so on. So maybe I will just state a theorem on this, or I'll just tell you, is there some method to this, Okay, maybe one simple example where you can already see this is think about this density matrix. So let me just think about the two-dimensional case, okay? Think about a two-dimensional quantum system, and actually let's go back to the Stern-Gerlach itself. So let's think about a single spin-half system. And I can think about one density matrix, which I call rho 1, which is half, which is an equal mixture of the spin Z eigenstates, okay? And another density matrix, which is an equal mixture of the spin X eigenstates. If I were to now actually write down a representation for these, okay, meaning I represent these typically as some column vectors and so on, right? This is some 2 cross 2 matrix. This is some 2 cross 2 matrix. And maybe it is easy for you to see. So are these two matrices the same or are they different? So this is a pair of orthogonal projectors which spans the space. This is another pair of orthogonal projectors that spans the space. So what do I expect when I sum these two? What do I expect when I sum a pair of orthogonal projectors that span the space? What should projection to plus z and minus z sum to? Identity, right? Yeah. So this is actually what we like to write as I by 2. And of course, this is also I by 2. Yes? So this is the simplest sort of example where you can see that the same density matrix. So the identity operator in itself cannot constitute a valid density matrix or cannot constitute a valid quantum state because it is not trace 1. You have to normalize it, and that's why you put the dimension here, right? So these kind of states are called maximally mixed states. I can extend this idea. So in a d-dimensional setting, I can think about this I by d state. Okay? It is think of some orthonormal basis in d dimensions, right? That's a decomposition of identity. There are, of course, several decompositions of identity, so there are several ways to decompose this. And this state is what one calls a maximally mixed state for obvious reasons. You are now in a uniform mixture of this set of orthogonal states. So you already see that this representation of a density matrix as this ensemble is not unique, right? And of course, the most pathological example of that is this maximally mixed state, which admits infinitely many such decompositions, right? As many bases as you can construct for the space. Now, more generally, for any density matrix, I'll just state this nice result about the connection between different pure state decompositions. I will not even try to prove it. And then I will discuss a little bit more about pure states and mixed states and maybe define the von Neumann entropy. Okay. So let's assume that there are two such decompositions. What this nice result tells you is that there is a way to relate.
Ma'am,
Yeah.
how did you make the convex mixture from those eigenvalues, EI? That I didn't understand, because EIs can be negative.
Oh, but I started by, so now I'm going the other way around, like I said. I started with saying that this is a positive semi-definite operator of trace 1.
So those eigenvalues are not the actual eigenvalues.
Of what?
Like we had the eigenstate, and it has some
Of
eigenvalue.
some observable. So
Yes.
the way I built up the density matrix was to talk about a measurement, an observable, and the eigenstates of that observable.
Yes.
Okay? So that was one way to get the density matrix. Yes? This is starting from a positive, any positive semi-definite operator.
Okay.
I can always write down a spectral decomposition. So I'm just trying to complete the picture. I'm saying that you realize a density matrix like that. So if you want to talk about that specific example, yeah, where I had some observable A, and then the final state was this density matrix. I started with some initial pure state. The final state was this mixture. Right? So this is, if you will, a physical way of getting to a density matrix. Now I abstract out its mathematical properties. And I said that this is, you look at this, you realize that this is a positive matrix. You realize that it has trace 1, right? So now I'm looking at the set of all positive semi-definite matrices with trace 1, and I'm calling them density operators. And now I'm saying, can I pick any arbitrary positive semi-definite matrix of trace 1 and associate an ensemble with that? Yes,
Yes.
through its eigen decomposition. Okay? Yeah.
Sorry, could you please clarify in what sense are the states maximally mixed? Why are they maximally mixed?
Yeah, they are maximally mixed. Will become clear when we talk about the entropy. Okay, so maybe just give me another 15 minutes and we'll talk about why they are maximally mixed. Intuitively, you can just think about this as it's a two-dimensional system, right? I'm allowed at most a pair of orthogonal states, right? And now I have a state which describes a situation where either of these orthogonal states could have been picked with equal probability, right? If, for example, I had a density matrix of this kind, no, sorry. Yeah, what did I say? This is a different density matrix, right? I call this something else, noted down. Now this, on this state, if I were to perform a measurement in this basis, you realize that a certain outcome is more likely than the other. This is no longer as unbiased as this decomposition. So this is a case where you are not maximally mixed because you have a probability distribution which is biased in favor of one of these outcomes.
So in statistical physics terms, it means that we have no preference between any microphone.
Absolutely. Yeah, yeah. You can think of this as, yeah, in a microcanonical sense, you can think of this as all these states are equally likely. Exactly. Yeah. Yeah.
Can you also tell me that positive, I understand, but what do you mean by semi-definite?
Yeah, semi-definite, very loosely speaking, I'm not going to define this formally, is to say, for example, I could think of a scenario where this, or let me go back here, where this matrix is not full rank on the space. So it could have some zero eigenvalues. So that's all I mean by that. Yeah. Okay. Right. So I wanted to talk about yeah, equivalent decompositions of a density matrix. Right, so this is a result which is credited to many people. So I'm just going to call this the SHJW theorem. The S here stands for Schrodinger. Well, if you pour through his works, you realize that he did have this notion that the same density matrix could have multiple pure state decompositions. And more recently in the quantum information literature, this is due to Houston, Josa, and Bouters. So the idea is the following. Suppose I have two ensembles, okay? One with probability distribution, which I call Pi, and a set of pure states psi I, okay? And then I have another ensemble with a different probability distribution Qj and states phi j. I mean, I don't need, I could, so yeah, you'll find that I kind of alternate between these. I either write them just as pure states or I write them in terms of the projectors. Of course, these are rank 1 projectors. Okay, a very quick aside, which I wanted to say even earlier. I wrote down all of this measurement discussion and everything, assuming that you have rank 1 projectors, but that need not be the case. The entire discussion goes through where I could think of an observable which has a degeneracy. So the set of projections that I associate with the eigenstates need not have rank 1, right? And still this entire discussion will go through. I can still think of the measurement as this set of projections, not necessarily rank 1, but having the property that they sum to identity, that they are mutually orthogonal, and so on and so forth, right? So just to clarify that there's nothing that is special that they need not be rank 1. Of course, when you want to do a decomposition, then you're going to pick a particular set of eigenstates for that and go about this, right? Okay. So our two ensembles are associated with the same density matrix, so they represent the same density operator rho if and only if they are related, particularly this the weighted superpositions of these states are related as follows. So I'm just going to state this here and then explain what that means. So basically I should be able to realize one of these sets as a linear combination of the other set with unitary coefficients, okay? So sum over j, uij, okay? So this uij is the ijth element of some unitary matrix. So if you're interested in the proof, maybe if we have time during the tutorials, we can try to discuss how to prove this. But the idea is that multiple pure state decompositions can give rise to the same density matrix, provided the set of states in these are related to each other as a linear combination like this with unitary coefficients. There were questions, yeah. No. The numbers need not be the same. You have to append, yes, you have to append zeros and ones accordingly to complete the unitary matrix. So I could have different sets. So I could go from 1 to n, j could go from 1 to m, okay? And I then just append the necessary zeros to make this a unitary matrix. Yeah.
Yeah, so earlier you had a measurement operator. The number of measurement like outcomes were exactly equal to the dimension of the Hilbert space.
Correct.
And the reason for that was that the operators had the rank
The observable was full rank is what I assume. Yeah,
Okay.
yeah. If it was not, then again I would have some zero probabilities, which is why one often defines the density matrix more precisely as positive semi-definite rather than just positive, okay? All right, so this is just a nice result to keep in mind, and if time permits during some other session, we can try to prove this, but I urge you to think about this. one way is very easy to show, right? So if you start from here and write down these kind of sums, right? Write down sum over qj, phi j, sum over I, p, I, psi I, you should be able to show that they are the same. The converse direction requires a little bit more work, but the hint to do that is to go through this, the spectral decomposition. So every density matrix has a spectral decomposition, and through that, you can now relate it to two different pure state decompositions and show that those pure state decompositions must be related via some unitary matrix, okay, via coefficients drawn from a unitary matrix. Okay, so this was pretty much what I wanted to say about density matrices. Any more questions on that? If not, we'll talk a little bit about the entropy in the last 10 minutes or so that we have, and then talk about bipartite systems in the afternoon, okay? No, no, you don't have to assume anything, just pure states. So when I say two ensembles, I just mean that the norm of, the inner product of psi I with psi I is 1, and inner product of phi j with phi j is 1. So I'm just assuming that they are pure unit vectors, that's all. So this is all that I'm assuming. I'm not saying anything about even, you know, within this decomposition also they need not be orthogonal, right? Psi I and psi j within this, or psi I and psi k here need not be orthogonal. Phi j and phi m here need not be orthogonal, okay? Maybe let me just give you an example of this to show you that this is possible, okay? Yeah, it's okay. I think we have a little bit of time here. Of course, the example I gave you here, the maximally mixed state, is very, very special because all these decompositions are orthogonal decompositions, right? So it may give you a very wrong idea that they're all orthogonal. So that's not the case. So here's a simple example, again in 2 dimensions. So think of this density matrix, which is a mixture of these 2 states, which I'm just calling 0 and 1, okay? Now I define 2 other states. So in this case, let's say 0 and 1 are orthogonal, okay? But, I'm sorry, I think. Yeah. So this is a pair of pure states which you can check are not orthogonal, okay? And you can see that actually this rho will be I think an equal mixture of A and B. So this is something you can check. So it's the same density matrix. This you could think of as its spectral decomposition maybe, right? This is a decomposition in terms of a pair of orthogonal states. But there exists another pair of states whose inner product is not 0, okay? And you can realize the same density matrix as a combination of these 2, as a mixture of these 2, right? So this is just an example to say that you don't need orthogonal decompositions. These pure states need not be orthogonal to each other. In the case of this theorem itself, neither of these decompositions needs to be in terms of orthogonal states, okay? All right, so I hope I've now given you a sense of pure states versus mixed states, right? And the need to also include mixed states in our description of quantum systems. Given an arbitrary density matrix, how do I know if it is pure or mixed? I'll just give you an example here to say why this is not a trivial question, Okay, what do I mean by saying I give you an arbitrary density matrix? So here, for example, let's say I give you a 2 cross 2 matrix in this sigma z eigenbasis, okay, which looks like this. Is this a density matrix? Okay. Ah, so now you're bringing in some new elements. You're talking about rho squared. Yeah? Okay. And what did you observe here? For? Oh, this is about the question that I asked. Ah, okay, yes, you're answering that question, absolutely. Okay, okay, so I leave it to you to tell me if this is a valid density matrix. And if so, is it the density matrix associated with a pure state or a mixed state? So what do I mean by that? So let me just say this. So when my system is in a pure state, psi, a unit vector, right? I can write down a density matrix associated with this. Essentially, what is the ensemble that I'm talking about? I'm talking about an ensemble with a single state which occurs with probability 1. So the same framework which I introduced, this ensemble picture, I should also be able to retrieve my pure states as a limiting case of that, right? And the way I do that is now this is for me a collection of just this single, it's a singleton set. It's a set which has just one element which is occurring with unit probability. So what is the density matrix that I associate with this? I will call this some rho subs. Yeah? Right? If I had more states, I would then sum them up like this, rank the projectors onto those states with the weighted probabilities. But I now have a single pure state, right? So basically it's an ensemble with a single element. So this is the density matrix that I associate with this. Okay? So this is a pure state density matrix. And if I instead have some collection like this, some pi's and phi i's, then I have a different density matrix, which is now a mixed state density matrix, which is this. So what properties distinguish for me this from this? And as someone pointed out, you can think about this essentially is a projection, right? The pure state density matrix is a projection. And so you know that when I square this projection operator, I get the same operator. So this fact that rho squared so I'm going to ask, is it a density operator first of all? And is it pure or mixed? Okay? So maybe you can tell me this in the afternoon. So by asking this question, what I mean is there associated with it a single pure state, or is it a mixture of this form, right? And one way to check is to realize that rho squared is equal to rho for pure states. Okay? So what about mixed states? Now when I have a state like this, when I write down rho squared, so I'm just to distinguish this, I call this by some sigma, right? So let me write down sigma squared. I hope you see that what I get is simply this. So let me assume for simplicity that in this case the phi i's are orthogonal. Okay, so let me say that this is that phi I, phi j is, I'm sorry. Okay. I always have such a form for any density matrix. That's a spectral form, right? So let's say that this is the spectral decomposition of this density matrix, then sigma squared you realize is this, and you then realize that trace of sigma squared is okay, because each of these is one of a set of orthogonal states, rank 1, okay. So each of them has trace 1, yeah. So this is this. So in general, you realize that trace of sigma squared is going to be less than or equal to 1, okay, for a mixed state. So trace of sigma squared in itself can be thought of as a measure of the purity of a state, okay. When trace sigma squared is exactly equal to 1, you know that you are in this situation. So I'm sorry, maybe here I should just say less than 1 and say that in general trace sigma squared is less than or equal to 1 with equality if and only if sigma is a pure state. Yeah.
It is not sufficient to say if sigma square equals to sigma, then we can say that is not, sorry, let me reframe it. So if sigma squared is not equal to sigma.
Yes, yeah. So the difference between what I'm saying now and what you're saying is about checking whether something is a pure or a mixed state to asking how mixed is a state, okay? It's about witnessing purity in some sense versus quantifying it. So in one case, yes, it's a check to just check that this is true or not. But if now you want a measure of how close is this density matrix actually to a pure state, okay, or how mixed is it? And as someone asked me, why are you saying that something is maximally mixed? That implies that I have some notion of how mixed a state is, right? And you can see that I'm leading up to an entropy-like quantity, right? So the first entropy-like quantity I want to introduce is actually this, which is trace rho squared of a density matrix. In fact, I will define something called a linear entropy, okay? This is sometimes called S sub L of rho, okay, which is simply 1 minus trace rho squared, okay. Why is this an entropy? Basically, if I have a pure state, you realize that trace rho squared is equal to trace rho is equal to 1. So the linear entropy of a pure state is always 0. And because trace rho squared is always upper bounded by 1, it is lower bounded by 0, I have a quantity which is which is between 0 and 1, okay. Okay, the upper bound need not reach 1, so so let me just say that in a very worst case it could be 1, but there are, okay, maybe I shouldn't write this, so let me not say this. Let me say that it is less than 1, okay. So working out this upper bound is an interesting exercise in itself. Let me just say that this is something which is less than 1, and it is 0 if and only if it's a pure state, okay. So you realize that I've inverted this. I said trace sigma squared is a measure of purity. I'm saying now 1 minus that, right? In fact, trace sigma squared is a measure of, so 1 minus that to me is like an entropy, okay, which is basically 0 for pure states. It has some upper bound, which one can think about what that upper bound is for a particular dimension. Okay? Sorry?
It has convexity?
Yes, it does. So in fact, this belongs to this class of so-called Renyi entropies. And this can be related to the second Renyi entropy, just like how the von Neumann entropy can be related to the first Renyi entropy, which is the Shannon entropy. Okay? Yeah. What makes a quantity a good definition of entropy? Okay. So, yeah, maybe I went ahead. Since I was here, I thought I will introduce this linear entropy. Okay, so what does entropy supposed to represent for you? Your state of knowledge of the system or your state of uncertainty of the system? I don't know. How do you think about entropy?
Like larger it is, the more chaotic the system is something.
Okay, you're using words like chaos and so on now, which one will not get into. So let me say at least the way, let's say an information theorist would think about entropy, right? Let's say the way Shannon thinks about entropy maybe is about your state of knowledge or ignorance of the system, right? Either way, whichever way you want to think about it, right? And in the quantum mechanical context, with pure states and mixed states, I have a kind of demarcation of this already, right? If I have a pure state, when I write down a pure state, right? What do I mean by saying I write down psi? I'm giving you psi, let's say expanding it out in some orthonormal basis for you. It means that I have complete knowledge of the state of the system. Right? So from this sort of information theoretic point of view, I'm completely certain about this system. And so I think of such states as zero entropy states. Okay? And on the other hand, if I tell you that I have one of a set of states which can occur with some probability, then I'm now uncertain about the state. I don't have full knowledge of the state. Right? And if that set of probabilities happens to be a uniform distribution, so that's why I said this upper bound is not 1, because if you put in a uniform, a maximally mixed state, then this value will be something which is dimensional dependent, but which is less than 1, okay? Then that to me represents maximal uncertainty and therefore maximal entropy.
Then I say that pure state could be characterized by a vector, but a mixed state could be only characterized by a matrix.
Yes, indeed. A pure state, yes, could also be characterized by a matrix of this. Yeah. Yes, indeed. Yes, you answered the question. So this is indeed a pure state actually. Okay? Yeah.
Yeah, but what you said, like you have the definition which satisfies something on the two extreme ends, but what it does in between, does it not matter?
So you want a function that is going to smoothly take you between these two extreme values and in a monotonic fashion. Yes? Does that make for a good measure of entropy? Does that say that, so higher the value of this thing, right, the more uncertain I am about the state of my system. Okay? So indeed, any function which can satisfy these properties, I would think of as a good measure of entropy. Of course, people can correct me if I'm saying something. Yeah.
Typically, we use like convexity as well as like some arguments like that, right? For example, it needs, suppose I have a
Yes, no, I did not talk, yeah,
like
indeed. So there should be a convexity property that you associate with it, absolutely. So you want, so this is something that was mentioned in the previous lecture also, that when I take two states and take a convex sum of that, then my uncertainty about this has to be larger than the uncertainty that I have when I'm in these individual states, right? So of course there should be a convexity property that has to be satisfied. Sorry, I should also mention that.
Just a question regarding that convexity
Yeah.
property. Is
Yeah.
this linear entropy, does it satisfy that?
Yes, the linear entropy does satisfy that. If you want, we can discuss that offline. I was not planning to show that here. But yes, it is a valid measure of entropy in the sense that it is 0 for pure states. It increases between 0 and something which is less than 1, right, as you go from pure to mixed states. And it is something which is concave, right, which is what you expect from an entropy quantity. Okay? If you think about it in some sense, you are writing down the second moment of the density matrix. So maybe, yeah. Okay, so there's one more question. We can discuss von Neumann entropy, and I can show you maybe the connection between the von Neumann entropy and this in the afternoon. Yeah.
Do I understand correctly that this rho squared metric physically means that we have two consecutive experiments with the same observable and checking how different the result of the first metric measurements are with respect to the second one?
You could think about it that way. But it's not about consecutive, no, because I'm now talking about the square of the operator, okay? And this is, remember, the state. This is not the measurement observable, right? You're asking whether a state of a quantum system is pure or mixed. So this is, in a sense, a purely mathematical notion, right? How one can measure this entropy in an experiment and so on and so forth is a different question, right? For example, how do I actually get this out, right? Is this something that I can measure in an experiment? The one way to think about this is you do a spectral decomposition of rho, you get a handle of its eigenvalues, and then you will see that this is actually related to the fourth power of the eigenvalues. So if I think of a probability distribution, then this is actually giving me the square of the probability distribution. So that's what I was trying to say, that it is related to the second moment of a probability distribution or of a density matrix. So this is not something that you can think of as successive measurements and so on, because you're squaring the density operator, whereas successive measurement is a different sort of mathematical object that you would write down.
So according to this question, so we cannot think this rho square as a successive operator, successive measurement, because operator is written in terms of lambda is superposition and rho is written in pi superposition. So is it correct?
Yeah, see, a density matrix is in itself also an observable. So let's clarify that. Yes? Because it's also a Hermitian operator. It's just a Hermitian operator with additional special properties, like it is also positive and it is also trace one, right? But observing the same operator twice is a transformation of the state. It is not simply squaring the operator. That's what I want to clarify. So that's the reason I draw a box, right? If I want to think about measuring rho, for example, then I would write down a measurement operator that is associated with measuring rho. And that's a transformation of the state. That's a kind of, it's a map from state to state, right? That's what we saw. For example, it's a map that could take pure states to mixed states, right? So it is as if you're acting that map twice, which is different from saying I'm just squaring the matrix. Okay.
In the examples with the Stern-Gerlach, rho would be like the state of the system between like S.
Exactly. Yeah. Exactly. Yeah. So it is not the same as doing a measurement operation twice. Okay.
Just from the eigenvalues of this matrix, can we not say it is a pure or mixed state?
Just from the eigenvalues, how would you say if it's a? You need knowledge of the eigenvalues even to get something like entropy and so on. But I'm saying if you don't need to quantify it, you don't even need to go to the eigenvalues. You simply do this check. But just the eigenvalues themselves will not tell you anything. You have to compute a function of the eigenvalues. Like you have to compute this linear entropy, for example. Right? I mean, I don't know, in what sense did you mean that the eigenvalues will tell you? Because you have a 0 eigenvalue and 1, yeah, exactly. So in this case, yes. But in a more arbitrary setting, just having a set of eigenvalues is not... okay, so you're saying that if there's a...
If there is 1, 0 and like if we have 3 eigenvalues, if only one is 1,
Yeah.
everything is 0 is the pure state.
Yes, that is true. Yeah. Yeah, no, you're right. Yeah, that is true. So if I know that it's a rank 1 operator, yeah, then I know that it's a pure state. Yeah, sure. Okay, so maybe I should stop here and then we'll continue in the afternoon. Yeah.